Great. Yeah, thanks everyone for joining this seminar. The goal for this seminar is for us to kind of give you a high level overview of like all the tools we're building. So I'll kind of just start with a motivation of what we're trying to do. So as you know, AI these days are getting really powerful, and what we're trying to do is try to leverage AI as a design partner for photonics and electromagnetic simulation. So imagine a world where you can really focus on solving the most challenging electromagnetic problems, and the barrier to accomplishing those tasks are very low. And to that goal, we here at Flex Compute and all our products, we've spent a lot of time, building really good interfaces. We have very good Python API in Tidy3D. We have GUI interfaces to interact with your simulations. We spend a lot of time building these example notebooks that the users can kind of take as a reference and use that to build and modify that to build your own design, right? Um, and so the goal for using AI is to make that process even simpler. So you can really focus on physics and solving your problems. And AI, AI assisted designs, currently the LLMs that you kind of get from major vendors like OpenAI, um, Anthropic, they're already quite powerful because they've been trained on a lot of publicly available data on the internet, right? Um, and you can do things like ask it about photonics. Yeah, there's a lot of it's a general purpose AI tool. And so right now, I did this exercise just yesterday. If you ask it, okay, can you help me set up an inverse design of a grading coupler in Tidy3D? Well, it does do a lot of work in the background. So it almost thought for 1 minute, 31 seconds, does some Google search and whatever it does to then give you, not just like, okay, here's how you should set up the code, you should set up the simulation, but also here's the code, right? But then in practice, if you take that code and try to run it, which I tried to do, you can already see lots of problems. So one of the things is that, well, this kind of the LLM was probably trained at some earlier point in time. So it's using a plugin that's already our legacy, right? So we've already moved to AutoGrad from JAX. There's a lot of hallucinations as to, so it's picking some name for the material library, but when I try to run it, it says, oh, we don't have that. It's actually crystalline silicon in our case. You also run into a lot of errors from purely it kind of hallucinating on what the API should be to set up a mode source. And go and I can go on and on and on. And I think this is the part that creates a lot of friction when you try to then use AI to solve real problem. Because the problem that you're trying to solve is build an inverse design of a grading coupler, but then you run into all these issues, right? And so the question is, how do we kind of make this better? And so what we're doing, so we've been working to provide you with all the tools to to get to your design faster. But now we're also building tools to provide AI agents more context, more in-depth resources, up-to-date information, and also give it visual feedback. Because when you're building simulations, you got to see what you're building. So essentially, in today's talk, Emerson will walk you through a live demo to show you these three different aspects. So one is the live MCP server, where the AI can access up-to-date docs, APIs, example libraries, lectures, tutorials, and this spans across, multiple products, our Tidy3D product, Photon Forge, RF. There's a really nice viewer so that the agent can kind of see what simulation it's building. And then also there's a lot of work that went into kind of building this domain knowledge so that the AI agent it knows about Tidy3D specific workflows. And this is equally important as, all of these other tools that we're building. And we've also made the process of kind of using it incredibly easy for you. So what you need to do is you can just pick your favorite IDE of choice, like VS Code or Cursor, click on the extensions, you search for Tidy3D and basically install that. And then the rest is, there's a process of how to get it started, which Emerson will cover in detail. And I'll pass it over to Emerson now for the actual demos.
Thanks for this amazing presentation, Prash. Now I will demonstrate some use case for the Tidy3D extension. The extension is available for both Cursor and VS Code. In this demonstration, will focus on its usage in Cursor, which is an AI-oriented development environment, but the experience using VS Code and GitHub Copilot is quite similar and equally powerful. Well, to start using the extension, you need to install Cursor. You can obtain a free, although more limited version from cursor.com and get a Tidy3D API key, which you can also obtain for free from simulation.cloud. So after opening Cursor, go to the Extensions tab and search for Tidy3D. So you can click on the Tidy3D installation and then you can follow the quick start guide instructions and install the extension, or you can also look at the complete installation instructions if you also would like to install a local Tidy3D environment. So when you open a Tidy3D related file, the extension will prompt you to run the workspace setup command, which you can also manually trigger by pressing Ctrl-Shift-P and searching for Tidy3D. So the extension configures the FlexAgent MCP that you can find here. So you can see it's enabled, and it also configures a Tidy3D 3D viewer that you can find here in the status bar. The viewer automatically detects Tidy3D simulation definitions. So when you open a Tidy3D related file, you are going to see a notification here in the status bar. And then you can click it and open the 3D viewer. When you run the Tidy3D workspace setup command, it installs the FlexAgent rules under cursor/rules. So these rules are applied to all your prompts to help manage the context and define how the assistant operates for Tidy3D simulations. The most important point to highlight in this file is the definition of specific sets of rules that tailor the assistant behaviors to specific scenarios, such as learning, troubleshooting, customizing a simulation setup, creating a simulation from scratch, or analyzing simulation results. In addition, there are key principles like processing tasks sequentially, avoiding common pitfalls, and following geometric guardrails, and another series of general instructions that applies to all those scenarios. So in summary, these rules ensure the assistant provides accurate, efficient, and physics-aware assistance while keeping you in control at every step. It will not make changes, run simulations, or proceed without your approval. So you are always the decision maker. And this is important because despite all the recent advancements in LLM models and MCP integrations, they are still probabilistic models, and as such, they are not 100% error free. Well, now let's explore mood analysis workflow. We will cover how to quickly start a new chat, build a solid context, and create a mode analysis from scratch. Let's come back to cursor. So in my experience, better results can be obtained when you start your chats by explicitly asking the assistant to follow the FlexAgent rules. For example, in the next prompts, strictly follow the rules in FlexAgent file. These rules have priority over rules in other files. So this is a good practice to prevent potential conflicting rules from other sources. When you repeatedly start chatting this way, at some point cursor will add it to its memory and automatically apply these prompts to our chats. Here we can verify the LLM has identified the FlexAgent file, and here we have a summary of those scenarios: learning, troubleshooting, customizing a simulation setup, and so on. And we also have a summary of those general principles that we want the assistant to follow. So my final goal is to build an edge coupler here. And a mode overlap analysis is the first part within this broader design workflow. It's also a good practice to prepare the environment to ensure the assistant is aware of your goals and to verify whether it has a basic understanding of the subject you are interested in. So the richer the context, the better the response. So I'm going to ask general questions about edge couplers. For example, I'm interested in PIC device simulations. Please explain me what what a edge coupler is. So here we can see the assistant is reasoning, trying to understand my prompt, and now it connects to FlexAgent MCP and runs the search flex compute docs tool. So it is searching for accurate information about edge couplers. In a few seconds, we can see the output. So here we have a summary about what is an edge coupler. An edge coupler is a fiber to chip coupling device that enables efficient transfer of light between an optical fiber and a photonic integrated circuit. So we have information about the coupling challenge, basically the mode size mismatch between a huge single mode fiber, real mode field diameter, and a very small uh, integrated waveguide mode. So we have the information about how edge couplers work. Edge couplers use adiabatic mode transformations, so it's all useful information. We have some common design variants like single layer inverse taper, bilayer edge couplers. We have a comparison between edge couplers and grating couplers and a minimal code example to set up an edge coupler simulation. And finally, we have some key design considerations like taper length, tip width, and so on, and some reference in the end. So This is an example of the learning workflow in action. Now let's continue with another question related to Tidy3D. So how can I calculate the mode overlap between a Gaussian beam and a waveguide mode using Tidy3D? Give me some examples. So again, the LLM is reasoning. It connected to FlexAgent MCP again to search for accurate information. It's running another tool from FlexAgent MCP, the Flex Compute dot, to retrieve information from a specific file in our documentation. Okay, we are almost there. So now we have information about how to calculate a mode overlap between a Gaussian beam and a waveguide mode using Tidy3D. So here we have the definition of the mode overlap, information about the alter dot method, which we can use to calculate the overlap integral. And here we have some examples. Here we have a basic mode overlap calculation. So here a Gaussian beam profile component is defined, and then we have the definition of a mode solver simulation. Okay, in the calculation of the mode overlap. In this second example, we have an example of a parameter sweep to sweep the waveguide width and calculate the mode overlap. Another example about misalignment tolerance analysis and some final tips. So after setting this foundation, I will begin to create the simulation workflow. So let's write, I want to build a simulation workflow for an edge coupler device design. I would like to start with a mode overlap analysis to verify the ideal taper tip width. Okay, so I expect the assistant can correctly identify one of those scenarios, and then after identifying those scenarios, I should be guided through some steps to build this simulation workflow. So again, it calls the FlexAgent MCP. And here I have some information about my requirements. So I can double check here if it correctly understood what I've asked here. And I have some clarifying questions. So before start building the model, I need to provide this information. So let's see here we have uh, the assistant asks for materials, for operating wavelength, fiber specification, and taper design parameters. And finally, I have an option to let the assistant quickly build the complete simulation workflow for me using reasonable default parameters. And the option B, the assistant can guide me step by step through each component definition. So please provide the information above, or I can proceed with common SOI parameters like 1.55 micrometers wavelength, SMF 28 fiber, and so on. So let's provide the assistant the information that let's confirm this information. So for item 1, we can select SOI material platform. Item 2, operating wavelength of 1.55 micrometers and range between 1.5 and 1.6 micrometers. Heading 3, let's select inset fiber with 2.5 micrometers mold field diameter. Heading 4, let's select taper width range between taper tip width range between 130 and 230 nanometers with 10 nanometers steps. Okay, the last item 5, let's select option A. Okay, we are good to go. So the assistant will analyze my information and now it is going to guide me in the second step, the setup of the work environment. So to proceed, I need to know your preferred working environment. Option 1, create a new Jupyter notebook, or option 2, create a new Python script. So let's select option 1, create a new Jupyter notebook. Okay, so now it started to create a new notebook, and in the meantime, let's take a look in another case. So now we have now while the LLM creates the new notebook and populate it with code, let's take a look in a meta surface case. So this time I'll use the FlexAgent to analyze simulation results from different simulation setup. In this case, let's use the VS Code, the VS Code environment. So here we have the VS Code in the GitHub Copilot interface. And this is the MetaSurface notebook. I've already run the simulation. So we have simulation results here in this scene data variable. And I've already prepared this environment to save some time in this presentation. And I'm going to ask the assistant to calculate the absolute values of reflectance and the transmittance data sets, calculate the absorptance and plot all of them in a single chart, calculate the resonance wavelength and also display it on the plot. So let's hit enter. So the process here is quite similar to cursor. The assistant is reasoning. It will read the metasurface absorber notebook, and it understood my requirement, and it will start it will start with the data analysis workflow. So in step 1, it has analyzed my request. In step 2, proposed actions. Here we have a summary what is going to be implemented. So it will extract flux data from the reflection and transmission monitors, calculate the absolute values of reflectance and transmittance, calculate the absorptance, find the resonance wavelength, and create a single plot showing the reflectance, transmittance, and absorptance. So that's what I want. So I want to proceed. So yes. Now it's going to call FlexAgent MCP again to get accurate information on how to create this plot. Great, so it has included a new cell here. So this new cell extracts the reflectance and transmittance data sets. It calculates the absorptance value, and it finds the resonance wavelength and creates the plot. So we can accept this new cell, and now let's run this cell and take a look on the results. So here we got an error, and this is a good opportunity to demonstrate the troubleshooting workflow. So the error is related to the dimension mismatch. So it happens here in this line. So let's try to use the flex agent to help us solve this error. So we can copy the error message, and I'll ask the assistant to help me fix this error. Got an error when creating the plot, and I'll give it the error message. Let's see if it can correctly find the error. It is running the FlexAgent MCP. Okay, it found the error. Great, so it is proposing to convert the reflectance and transmittance datasets into NumPy arrays after extracting this data. So let's accept this fix and run the code again. And now it works. So it has correctly identified the issue and it correctly proposed a solution for me. So here we have the reflectance, the transmittance in green, and the absorptance in red. And the resonance is correctly identified as the absorptance peak in this chart. So here I have demonstrated the data analysis in the troubleshooting workflows. Well, do you remember we left the LLM working on cursor, right? So it has concluded the work. Here we have the edge coupler mode overlap notebook in the final in the in, after implementing the whole notebook, we can take a look on the code. It has implemented, right? It has included the library definitions, the simulation parameters, material definition, and so on. It has created the Gaussian beam profile, created a function to generate a mode solver object for different deep widths. Here we can visualize the mode solver setup, and it has created a parameter sweep using a simulation batch. And here we have the calculation of mode overlap and a series of cells to analyze the results. So we are going to accept all these chains. And now let's run the notebook. So we have the central wavelength, the material, silicon, silicon dioxide, the simulation parameters, Gaussian beam was generated. Now let's plot the Gaussian field profile. Here we can double check the mode field diameter. It seems correct in 2.5 micrometers. And here we have a cross-section visualization of the mode field distribution. Now let's run the simulation. Before running, let's visualize the simulation setup. It's okay, it's great. And now I have created the batch, the simulation batch. And now I'm going to run the mode solver. I'm uploading the simulations into the cloud, uploading the 11 simulations into the cloud, and in a few seconds they have run and the simulation is complete. Now I'm going to download the simulations from the cloud. In a few seconds, it should be ready and we can analyze the simulation results. The cost for running these 11 mode simulations is well below 1 Flex credit. We have created a very long workflow with a few prompts. We have created a complete workflow with lots of cells. Okay, it's okay. All the tasks have been downloaded. Now let's calculate the mode overlap. So it is going to use the outer dot method to calculate the mode overlap between the Gaussian beam and the mode data fields. Here we can verify the max coupling efficiency for each of the waveguide widths. So here the maximum coupling efficiency it's taken at any wavelength. We are not specifying a specific wavelength to read the coupling efficiency here in this output. So we can verify the coupling efficiency increasing from 130 to 109 nanometers. And now it starts to decrease. Okay, now let's obtain the optimal waveguide width. In this case, considering the central wavelength. So at the central wavelength, the maximum coupling efficiency is about 0.98, and the optimal taper tip width is 180 nanometers. Now let's plot the coupling efficiency versus tip width. We have two very nice charts. In here we have the ideal taper tip width. Here we have the coupling efficiency. In here we have the coupling loss in dB. Let's plot the coupling efficiency for all the taper widths, so we can compare the coupling loss for the different simulations. So it has created all these nice charts for us. Now let's plot the coupling efficiency versus waveguide width and wavelength. another interesting plot. So here we have the wavelength, the taper tip width. Now let's visualize the optimal waveguide mode profile. Let's analyze the optimal waveguide mode. Here I'm going to plot a lot of different charts. We have the optimal waveguide mode. The plot is saturated because the field value was limited in 4. And here we have the Gaussian beam profile, so we can compare the optimal waveguide mode and the Gaussian beam profiles, and we can observe some similarity between these modes, and that's why the coupling efficiency is so good. Here we have a cross section overlapping the Gaussian beam and the mode field profiles. And here you have a chart with effective index versus wavelength for the waveguide width of 180 nanometers. And finally, we have a final cell to summarize all those parameters. Great, so we have concluded the mode overlap analysis. So now we have the optimal taper tip width, so we can ask the system to create a full 3D FDTD simulation to obtain the coupling efficiency from a lensed fiber into an output silicon waveguide using an eddy coupler. In this last case, I'm going to highlight some additional points related to FlexAgent usage and demonstrate the 3D viewer. So let's move back to cursor and let's open another project. Is initiating. So I have already created this final simulation. This is the final notebook. To save some time here in this live demo, I've already created the notebook, and here we can visualize the complete simulation setup. You can visualize the simulation setup for a taper length of 15 micrometers. Here we have a cost estimation, then we run the notebook, and we have the result analysis also generated by the assistant. So here we have a peak coupling efficiency of minus 0.62 dB at the central wavelength. You have the plotting of coupling efficiency versus wavelength. So you have the coupling efficiency in dB, and here we have the coupling efficiency in percentage. And we can visualize the field distribution along the taper length and the field distributions at the input and output taper cross sections. Finally, we have a summary. Of the simulation. So this is the notebook it has generated, and here we can also visualize this simulation setup using the 3D viewer. So in the status bar, the viewer has identified the simulation definition, And we can click here and click here to open the viewer, or we can ask the assistant to open the viewer. For example, open the 3D viewer. So now it is going to ask the FlexAgent MCP to open the viewer, as we can see here. Let's hide this sidebar and increase the viewer's window. So here we have the viewer, and we can turn off the cladding and visualize the taper profile. Here we can click the simulation components and obtain information about each of these elements. We have this 3D cube where we can select a specific face, and we can also ask the assistant to set a specific view. For example, set the top view. So the FlexAgent is going to rotate the viewer and select the top view. So we can inspect the taper profile here, and we have a summary of what is supposed to be visualized in this view. So from this angle, you should have a clear bird's eye view of the quadratic taper profile, the 50 micrometers taper length, the source and monitors, and it asks if the geometry looks correct. And if everything looks correct, we can proceed to estimate the cost, run the simulation, and so on. So the nice thing about this integration is that the viewer becomes like the MCP hands and eyes. In future versions, you will be able to ask things like measure the gap between this ring and this waveguide, or save the top view to a file, or hide this structure, and so on. Let's quickly look at the conversation here. So this is the prompt I've used to create this notebook. Build an FDTD simulation to obtain the coupling efficiency from a lensed fiber into a 500 nanometers width silicon waveguide coupled through a quadratic profile edge coupler. So it has correctly identified the the create from scratch workflow, and here we can see some clarification questions. So in step 1, the assistant gave me the option to create the entire simulation workflow from a similar example. It has identified this similar example in our knowledge base, and it gave me the option to quickly create the complete simulation setup following that example, or the option B, guide me step by step through the setup process. So whenever it recommends following a Tidy3D example, it's interesting to accept that, because that usually ensures you can quickly get a functional setup which you can easily customize to your needs. We can also see additional clarification questions, and here I asked to follow. I asked to follow the typical parameters values from the example, but also asked to set the taper length to 50 micrometers and the taper tip width to 180 nanometers. So we've successfully implemented a complete design workflow for an edge coupler device using the FlexAgent MCP. We can expand this workflow by adding a parameter sweep or taper on taper length, optimizing the taper profile, or exporting the layout to GDS, among other options. So some final remarks. We've spent a lot of time testing and optimizing the FlexAgent, and we are excited to share what we've learned so that you can also succeed and enjoy using it as much as we do. It's important to understand that this assistant isn't meant to replace you. Instead, it is designed to be your partner, helping you move faster, learn more effectively, and boost your productivity. These are There are many tasks where it performs exceptionally well and provides reliable, error-free results. For example, if you want to learn about the Tidy3D API or simulation workflows, it's an excellent teacher. It also handles practical setup tasks efficiently, such as adding multiple boxes with defined sizes and positions for post-processing. It can generate clear, well-formatted charts for your fields, parameter sweeps, mode analysis, and more. It can assist with troubleshooting, help identify the root cause of issues, and guide you in customizing existing simulations, whether by adjusting parameters, modifying components, or expanding workflows. For instance, adding a parameter sweep or optimization to a base simulation. Some activities, however, may require more back and forth interactions when building complex workflows from scratch, such as creating an inverse design. The agent can do a solid job, but it's unlikely the first draft will be completely error-free. Similarly, when designing intricate polyslabs, you may need to iterate through a few prompts to get everything just right. Even in this case, the agent remains a valuable collaborator. In a few prompts, you can troubleshoot an issue, as I've demonstrated here in the data analysis example. For additional tips and best practices, check out the extensions README file. And this is the first release of the Tidy3D extension, and we'll continue improving it over time. So your feedback is greatly appreciated. Thank you.